Welcome back, everyone. Today we are doing a deep dive into the Redis architecture. If you want to master the system design interview or build production-ready platforms, you need to understand the mechanics behind replication, quorum, and scaling. Don't forget to hit like, subscribe, and ring that bell. Also, take a moment to look at the companion website bitbytoken.com for foundational and advanced system design guides across software, data, AI, and ML. This is the website, bitbytoken.com. I'll also put this link in the description below. Now, this is again divided into four key disciplines, which is software engineering, data, machine learning, and AI engineering. You can look at several of these disciplines. These are further divided into fundamentals. And these fundamentals are further having, say, for example, you have Kafka. Most of these are actually having like basics, advanced, and expert. So for example, here in the Apache Sparks, there is a basic concept, advanced and expert. Similarly, we have example solutions for each of these disciplines. Here we are trying to build fraud detection and all of these various different kind of systems. Uh, do take a look at it. Please provide your feedback to this so that I can make it more robust and more informational. Now, coming back to our topic here, let's start looking at these blueprints. Okay, so today we start with the atomic unit in memory speed. The baseline reality is that memory is orders of magnitude faster than disk. A database read might take 50 milliseconds, while a Redis RAM lookup is sub-millisecond. Caveat: don't overcomplicate things on day one. We use Redis primarily because memory is fast. Everything else we discuss, replication, failover, persistence, it's just the complexity required to protect that speed. To scale out reads, we use a primary replica model. The primary accept both reads and writes, while replicas are read-only. Notice the red ink on async. The tiny delay between a write hitting on primary and copying to the replica is where production incidents are born. You must design your system to handle that potential for stale data. How does replication stay in sync? We use the engine bells, offset, and backlogs. We track lineage with a 40-character replication ID and position with a byte offset. If a replica reconnects and has the same ID and a same small offset gap, we can perform a cheap partial sync. If the gap is too large, we fall back to full sync, which forks the primary process and can destroy your performance. Always tune your backlog size generously. When it comes to durability, the default can be a trap. An isolated primary accepts writes silently with zero redundancy. The fix is the min-replica-to-write setting, which halts writes if your required number of replica aren't reachable. It's a classic trade-off. Do you prioritize availability for logging or durability for payment processing? Choose your poison. Then there is a failover dilemma. Split brain. If the primary goes silent, is it a crash or just a network partition? If you promote a replica blindly, you might end up with two active primaries and diverging data. Never trust a single automated server. We need a democratic process to confirm a crash before taking action. That process is the Sentinel Quorum. Sentinels monitor nodes and manage failover, and your client should ask Sentinels for routing. Never talk to Redis directly. Use the quorum formula, floor of n by 2 plus 1. Always use an odd number of Sentinels to break ties. 3 is a minimum, but 5 is the production sweet spot. The silent assassin is the async replication gap. Because Redis sends an OK to the client before the replica acknowledges the write, any crash in that microsecond window causes permanent data loss. For critical financial path, use the wait command to enforce synchronous replication. Just don't pay that latency tax on your page view counters. For massive spikes, beware the performance assassin, hotspot keys. On Black Friday, one key might get 50,000 requests per second. The cluster load might look fine, but that single thread handling that key will throttle and cascade timeouts. Use Redis CLI hotkeys to detect this. Monitoring the cluster average isn't enough. You must instrument per key traffic. To handle that, we use in-process caching, the fast path. The fastest network call is the one you don't even make. By caching hotkey in your app server memory, You bypass Redis entirely, but beware the thundering herd. If your L1 TTL expires and N threads all rush to reload the cache at once, you'll take down your database. Always use per key mutex logs during cache reloads. Another strategy for high frequency writes is key splitting. You can't cache a write, but you can distribute a single logical key across n physical keys to unblock a single thread limit. The trade-off? Read simplicity is sacrificed. You now have to aggregate all those shards when you read, introducing eventual consistency. For heavy read traffic, use infrastructure scaling with read replicas. Route known hotspot, read exclusively to replicas via a load balancer. This is often a zero code change solution if your infrastructure supports read-write splitting. Use the tools you already have before you go writing custom routing logic. Use this mitigation strategy matrix to choose your approach. Identify your primary traffic type, read heavy or write heavy, and layer your defenses accordingly. Mixed hotspots are rare, but when they happen, senior engineers know how to layer L1 caching, key splitting, and read replicas together. This is the production architecture. L1 absorbs repeated reads. Replica absorbs distributed reads. Key splitting decompresses writes, and Sentinels automate failure. This is what a modern, high traffic platform actually looks like. You now understand what every single wire in this diagram does. Engineering is choosing async replication in speed versus potential data loss. L1 caching is latency versus data staleness. Sentinel Quorum is automation versus split brain risk. Remember, there is no perfect system, only well documented choices. In an interview, the engineer who names the trade offs first gets the offer. What trade offs have you had to make in your own Redis deployments? Let me know in the comments, and don't forget to like, share, and subscribe. Until next time, have a good life.